Welcome everybody to our business math video clips. Now we're discussing limits. This is Magda Talib Al Hinai from Sultan Qaboos University, and I welcome you all to our presentations. Suppose we have a function x cubed minus 1 over x minus 1, and we want to find the limit of this function as x goes to 1. So we want to know what happens to this function as x gets closer and closer to 1. In order to do that or to understand that, let's start by taking values for x less than 1, and we get closer and closer to 1 from the left side. Also, we take values greater than 1 and we get closer and closer to 1 from the right side. So we do this in the following tables. So when x is less than 1, we take 0.8, we find the corresponding f of x, we take 0.9, we find the corresponding f of x, and so on until we reach 0.999, and we see that f of x is getting closer and closer to the value of 3. Now we do the same thing, but as x is greater than 1, we take 1.2, we find the corresponding f of x, 1.1, we find the corresponding f of x also, and so on, reaching 1.001, and we calculate the corresponding value for f of x. Again, getting closer and closer to 1 from the right side tells us that f of x still is getting closer and closer to the value of 3. If we try to illustrate this on the graph in the following animation, here's the x-axis and the y-axis, and we graph f of x, and then we see that getting closer to 1 from the left side, and so on, we are getting closer to 3. We do the same thing from the right side, getting closer to 1 from the right side, getting closer and closer, closer and closer and closer, we see that we are getting closer to 3. So as x approaches 1, f of x approaches 3. So we will say the idea of a limit rather than a definition of a limit. So we say that f of x approaches a certain number L as x approaches a, and we write this in the form of limit f of x as x goes to a is equal to L. We can make the values of f of x get close and closer to L as long as we are keeping x sufficiently close to a. If such L exists, then we say that the function has a limit. Otherwise, we say that the limit does not exist. And we are going to discuss the properties of limits. Suppose we have capital L, capital M, C, and K are all real numbers. And limit f of x as x approaches c is equal to L. Limit g of x as x approaches c is equal to m. Then the first property is the sum rule. The limit of the sum is equal to the sum of the limits. The difference rule, the limit of the difference of two functions is equal to the difference of the two limits. Again, we said provided that L and M exist. Also, we say the constant multiplication. So if we have f of x multiplied by a constant k, so we can take the k outside the limit, and there we have k multiplied by limit f of x as x approaches c, which is equal to k multiplied by L. We move on. The product rule, we have two functions f multiplied by g. Their limit is equal to the product of the limits. So the limit of the product is equal to the product of the limits. Again, the quotient rule, we have f over g. We take the limit as x approaches c. So this is equal to limit f of x as x approaches c divided by limit g of x as x approaches c, which is equal to L over m, provided that m is not 0. We don't want a 0 in the denominator. Number 6, the power rule. So the limit of f of x all power n is equal to, we can make the limit enter inside here. So this is equal to the limit f of x as x approaches c all power n, which is equal to L power n. N is a positive integer. The root rule, so we can make the limit go inside the root. So the limit of of the nth root of f is as x goes to c is equal to the nth root of the limit of f of x is equal to nth root of L, which is equal to L power 1 over n. Again, we have to make sure that if n is an even number, what's under the root has to be greater than or equal to 0. Now, if we have a polynomial p, the limit of the polynomial p of x as x goes to a is equal to p of a. Here we can plug in immediately the a for x. We move on and we see examples. We start with example 1. We give you the figure of the graph of the function h, and we tell you if we multiply the h by half and take a limit as x goes to minus 3, what will happen? You simply say the constant comes outside the limit, and we take the limit of the function itself and then multiplied by this constant. So we will have limit as x goes to minus 3 of the 0.5 multiplied by h of x. It's equal to 0.5 multiplied by limit h of x as x goes to minus 3, and we find this from the graph in front of us, and we simply multiply it by half. We move on to another example. We have the limit of 3x squared plus 5x minus 9. We want to evaluate the limit of this function as x goes to minus 2. So we apply either the property of, we have a polynomial, so we simply say this is equal to p of minus 2, or we do the properties, which is distributing the limit inside the brackets, because we can go ahead and calculate the limit of term by term. So here we have our solution. We have in front of us the p of x is equal to 3x squared plus 5x minus 9. And then we take the limit of this p of x. Again, we do the limits, we calculate the limits term by term. We see in front of us the value equal to minus 7, which is simply p of minus 2. Now we do another example, compute the limit. We have a fraction, so a rational function. In the numerator, there is a polynomial, and in the denominator, there is another polynomial. We want to calculate the limit as z goes to 1. So we take this to be equal to limit of a polynomial p divided by polynomial q. Again, we can say this is equal to the limit of the numerator divided by the limit of the denominator, provided that this denominator is not 0. So this is p of 1 divided by q of 1, again, because we are taking a limit of a polynomial in the numerator and another limit of a polynomial in the denominator. We want to make sure that q of 1 is not 0. Now we plug in the 1 and we do our computations. We arrive at 13 over 6. Compute the limit. We have limit x squared plus 4x minus 12 divided by x squared minus 2x as x goes to 2. Direct substitution tells us that we have an undefined quantity, which is 0 over 0. Whenever we have a 0 over 0 and we're having a rational function in the form of a polynomial in the numerator and a polynomial in the denominator, we need to get rid of the 0 factor. So we factor this. In the numerator, we have x minus 2 multiplied by x plus 6. In the denominator, we take x common factor, and here we can cancel the like terms, which is x minus 2. In fact, these are the 0 factors, so we need to cancel the 0 factors in front of us, and we get limit as x goes to 2, x plus 6 over x, and we plug in the 2 for x, so we get the answer to be 4. Another example, compute the limit. We have limit as h goes to 0. Again, a rational function. In the numerator, we have 2 into minus 3 plus h all squared minus 18 all over h. So again, if we plug in h, you will get equals 0, you will get 0 over 0. We need to get rid of the 0 factor, so we will open the square bracket in the numerator and we'll see what's next. So here we're opening the square bracket and then we will multiply term by term by 2. So we will see in front of us that there are two terms that the need cancel to add up to 0 or cancel one another. We have 18 and minus 18. So we will take these as 0 together. So here we are left with a limit as h goes to 0 minus 12h plus 2h squared all over h. We can take h common factor in the numerator. So we cancel next the 0 factor in the numerator and the denominator. So we're left with limit as h goes to 0 minus 12 plus 2h. This is equal to minus 12. Further we go and we see more examples. Example, compute the limit t minus square root of 3t plus 4 all over 4 minus t. Direct substitution shows that we'll get 0 over 0 whenever we plug in 4 for any of the t's here. So we need to cancel the 0 factor. In order to do this, whenever we have a square root, we always think of the conjugate. So we multiply and divide by the conjugate. We have here t minus the square root of 3t plus 4. So the conjugate will be t plus the square root of 3t plus 4. So we multiply and divide by the conjugate of the numerator. Next, we keep the denominator as it is, and we look at the numerator as a product of two brackets identically the same but with different signs. This gives us the difference between two squares. So the square of the first minus the square of the second, but the second is a square root. So squaring the square root will cancel 2 with the half, so in the exponent, so we'll be left with 3t plus 4 all divided by the denominator, which is the product of 4 minus t and the bracket t plus square root of 3t plus 4. Now we simplify the numerator. We see that there is a 0 factor. We cancel t minus 4 and 4 minus t, and we are left with a minus 1. So here we get t plus 1 in the numerator, and here is the minus 1 I said, into t plus square root of 3t plus 4. Now we substitute for any t here. With a 4, we get minus 5 over 8. Next, let's see another example. Given g of y equals y squared plus 5 whenever y is less than minus 2, and it's equal to 1 minus 3y whenever y is greater than minus 2. And we are asked to find limit of g of y as y goes to 6. Also, we need to find limit of g of y as y goes to minus 3. We start with a, and we say limit g of y as y goes to 6. We see that 6 is greater than minus 2, so we will take the definition of g whenever y is greater than minus 2. So we take the limit of 1 minus 3y as y goes to 6, and we plug in the 6 for y, we get minus 17. Next, we do number b. Here we have limit g of y as y goes to minus 3. Minus 3 is less than minus 2, so we take the definition of g to be y squared plus 5. As y goes to minus 3, this is a polynomial of degree 2, so we plug in minus 3 for any y we see in front of us, so we're left with y squared, which is minus 3 squared, plus 5, which is 14. We move on. Given g of x is equal to x squared plus 4x minus 12 all over x squared minus 2x. This if x is not equal to 2. And whenever x is equal to 2, we have g of x equals to 6. Evaluate the limit of g of x as x goes to 2. In this example, we will see that we're trying to make you understand that the limit doesn't mean substituting x 2 for x. Or whenever we have x goes to a doesn't mean that the limit is equal to the value of the function evaluated at a, whatever the a is. Let's see our solution. We will start with take into account that g of 2, if x equals 2, it is given clear in front of us, it is 6. Okay, now let's take limit g of x as x goes to 2. We will do this again by plugging in values so that you understand the concept of limits. And we want you to make sure that it is not the value of the function at x equals 2. So here is x and here is f of x. And again, we get closer and closer to 2 from the right. We calculate the corresponding f of x. We do the same thing, getting closer and closer to 2 from the left. And here is the corresponding values for f of x. We see that approaching 2 from the right or from the left, the function gets closer and closer to the value 4. So the limit is 4, but the value of the function at 2 is not equal to 4. It is 6. So let's see in front of us that, as we said, the function approaches 4 as x approaches 2. So let's see, this tells us that the limit is 4 and it is not 6. The limits do not care for what the function actually is equal to at the point in consideration. The limits are only dealing with what's happening around the value x in consideration, which is 2 in our case. The behavior of the function at 2 is not important, and it will not change the limit, because here at 2 the function is 6, but the limit is 4. And let's see the graph of our function. We have it here. At 2, the function is 6, so that's why we put this open circle on the curve. But the limit we see in front of us is equal to 4. Whenever we get closer to 2 from the left, the function gets closer to 4. We get closer to 2 from the right, the function also gets closer to 4. And with this piece of information, we end our presentation. You can go ahead and do the plugging of x equals to 2. If you put here 2, you will get 2 squared, which is 4. You will get 2 times 4, which is 8. 12 minus 12 is 0. You put the 2 down here, you will get 4 minus 4, again 0 over 0. Try to get rid of the 0 factor and solve it in the algebraic method we've been doing in the previous slides, and you will see that your limit will be also 4. So we move on and we see you in another video.